Welcome everyone to this JMP academic webinar, JMP for Teaching Statistics in Semiconductor Engineering Education. I'm Ross Matusalam, a JMP academic ambassador. I'm here to just host and manage Zoom today. Our presentation will be led by my colleague and fellow JMP academic ambassador, Kevin Pochner. To preface what we're going to see today, I think most or all of us are aware that the semiconductor industry is really big and growing and is considered by a number of folks to be maybe the defining industry of this century. At JMP, we know firsthand how important statistical skills are in semiconductor engineering and manufacturing. All of the 10 of the world's largest semiconductor companies use JMP. So every day, our own technical staff, we see how data analysis skills are really critical for career success in the industry. So today, Kevin is going to show us why JMP is a great tool for teaching statistical skills and problem solving to future semiconductor engineers. And that's whether they're being trained in a dedicated semiconductor engineering program or maybe in a more traditional major such as chemistry or physics or materials science or otherwise. And actually, before Kevin gets to that and shows us some JMP tools, we actually have a special guest that Kevin is going to speak with. Today, we have with us a university professor here in the United States who's currently using JMP to teach statistical methods to future semiconductor engineers. And so he'll share his thoughts with us. Now, before we get started then, I just want to remind everyone to submit any questions you have at any point in Zoom's Q&A window. Feel free to use the chat for general comments you would like to make to everybody, including your fellow attendees. But if you have a question that you would like answered, please use the Q&A. It helps us actually better monitor which questions have been asked and answered already and makes it more manageable to share those answers with everyone. But with that, Kevin, are you ready to kick us off?
I am. Can you see my screen?
Yes, I can see your screen.
Okay, perfect. And before we get to our discussion with the guest speaker, a few things I just want to point out at first, and Ross was alluding to this. So you'll get a copy of this JMP journal. We're going to post this and send you an email in about a day or two, letting you know how to find it. Ross was pointing out how common JMP is used in the semiconductor industry. And so I'll let you go to these links yourself to read about that. But the one I want to draw your attention to is these customer stories. And if you go to that link, you're going to see a large collection of stories where industry is talking about how they've used JMP in semiconductor. Now, some of them are interviews, some have little videos. They're not teaching statistical methods. They're really meant to give a high-level discussion of how these kinds of companies are incorporating a statistical culture to solve problems. I often encourage faculty to maybe use these in class, give it as a little reading assignment and a class discussion. I know you have a lot of content to cover in a course, but I know some faculty who use these stories, and I find it helpful because students get to start to think about what do they want to do with their career? Where do they want to focus? So encourage you to take a look at those. I always like to make sure I have links in the journal about our resources. And so we've got our short little how-to videos, instructional guides, the academic webinar library where we put up recordings of our webinars. And that's where the one we're doing today is going to go. We have enhanced data sets and case studies. In fact, I'm going to use some of these in my demonstration. One I want to draw your attention to with these online courses. We're in the process of making our courses available for free. And the reason why I want to point this out to you is these are all courses that we would teach out in industry. So they're multi-day courses. Now you can do a self-paced learning on your own online. And the reason why it's very valuable is we're creating content for you. So if you want to incorporate some statistical methods in your course, you can draw from our previously made lectures and course materials and data sets. And this just allows you to, maybe you have your students look at a particular chapter or section of some of these courses. So we're really trying to make it easy for you to incorporate JMP. So want to make sure you take advantage of that. And so our guest speaker today is Andrew Hoff. Andrew is a professor and graduate director of the electrical engineering program at University of South Florida. He has a doctorate in electrical engineering from Penn State University. And he has led and been the director of a variety of programs as it pertains to material sciences and chemical engineering. He's also participated and led a lot of workforce training programs with the state of Florida. His research is mostly in materials and chemical processes for semiconductor and biomedical applications. He's received various awards in teaching, and he's also a fellow of the Electrical Chemical Society. So what we're going to do, and I'm going to turn on my video here.
And Kevin, if you could maybe for the moment turn off your screen share as well so that your
Oh yeah,
face
good
will
idea.
appear large for everyone.
Okay. Perfect. All right. Okay. I look good at 9 in the morning here. Okay. So, Andrew, if you want to turn on your video so we can see you. Great. All right. Welcome, Andrew. So I'm going to ask Andrew a few questions, and mostly around, how he's learned about JUMP, how he's incorporated JUMP in his research work over the years, and how he's incorporating JUMP into this semiconductor program he's leading at USF. And as Ross pointed out, if you have some questions, post it, and maybe we'll have a little bit of a discussion with Andrew. Um, I'm going to try to wrap this up in about 10 minutes or so because I do want to spend the bulk of the session today on showing you JUMP and analyzing data in semiconductor applications. So we'll start with this discussion with Professor Hoff. So welcome, Andrew. And so my first question to you that I'd like you to kind of discuss a little bit is, when and where did you first learn about JUMP? And if you could talk a little bit about how you and your colleagues were using it.
I first learned about JUMP when we were collaborating with local industries to develop and expand their workforce. And the company was a semiconductor company, and they had typically statisticians online, but we were training personnel. They needed to greatly expand their operational personnel to just expand their capabilities and their process here in Florida. And so the state had an arrangement with the company. Anyway, so that was in the late 1990s initially. And I think JUMP was developed or first offered in the early 90s. But anyway, most of the development engineers or process engineers at that company use JUMP in their monitoring their responsibilities to monitor processes or to address customer concerns regarding products that were being sold, et cetera. So that was my first exposure to JUMP. I was working on some metrology issues with the company in general, and I found myself starting to learn JUMP at that time to address uniformity of metrology results on wafers that were in process.
Well, perfect, great. And so during that time, so you're saying you're going back to the mid to late 90s there. So, in the past 25, I guess 30 years, like what kind of changes have you seen in terms of how semiconductor companies are embracing the statistical sciences and incorporating it across the organization?
In the early days, in the late 70s, all we had available as process engineers was next day reports. Online metrology issues were documented in IBM punch cards. So, and then the next day we got a 24-inch, wide sheet of the process results or the metrology results from that day. With the advent of microprocessors and multi-chamber process tools, that has expanded greatly, where process engineers can monitor their process tools. They can monitor how the uniformity across 4 or 5 process chambers in a given process tool are responding. Our graduates who go to work in the semiconductor industry end up many times reporting back to me that they're using JMP for a variety of purposes.
Excellent.
So I think the online, the advent of the microprocessor, if you will, I remember watching a JMP video a couple of years back where yield for a particular manufacturing operation was developed around online switches that were in process tools. So I think the advent of electronics has made a big difference in the applications and the use of JMP online in semiconductor manufacturing.
Excellent. Now, we have a lot of folks that are joining this webinar from academia, so a lot of professors. So I think they might be interested. Could you just briefly share and tell us a little bit about the program you're creating? I know there's parts of it that are brand new and you're creating a specific curriculum. Just share with us a little bit, because you might give some ideas that some of the other professors that are joining might want to leverage.
Well, it's a semiconductor certificate. So it's a manufacturing certificate that we're offering online. It includes semiconductor physics, manufacturing issues, process issues, metrology issues, all the above. It's a 15-credit certificate in our graduate program.
And do you have a course that's fully dedicated to statistical methods, or are you working some of those concepts and methods through various courses?
I have a 1-credit course that's focused on measurements. When we teach processing, one of the issues is how we scale devices. So since the 70s, up through the 90s, devices were scaled just linearly, but now they're starting to have to apply other scaling methods. And in order to address those challenges in processing, people use design of experiments and typically statistical process control. So those are the things that I emphasize in the courses. And exploratory data analysis is another big discussion that we have.
Okay. And lastly, do you have any advice that you could share with faculty that are trying to do the same thing, incorporating statistics into their program, or maybe creating a full course on statistical methods? Anything you could share to help those folks do the same thing you're doing?
Well, take advantage of the online stuff that your company provides. There's a lot of. I mean, I'm not a statistician, but in order to impart the and discuss variation, that's a critical part of manufacturing. Um, they should take advantage of the online capability that in training that your company is providing. There's a lot of just a lot of basic statistics information. I mean, most of our students have statistics background, but they don't have statistics background regarding uh, Shewhart methods for process control or the other sources of variation that can happen in a manufacturing environment. So,
Yeah, I'm working with various faculty in similar programs, and they've shared with me, yes, the students may have had a statistics course and maybe two statistics courses when they were an undergrad many, many years ago. They certainly don't remember it. More of the challenges is those courses tend to be pretty basic, right? They're going to cover like one sample inference, two sample inference. They don't often have a lot of focus on design of experiments or quality control. And so I know faculty who are directing their students to our courses, and some of them are giving it as an assignment, like go participate in this course or these particular chapters of the course, because they don't have the opportunity to really devote a lot of time in the courses to methods. And so they're having the students go to our resources and learn on their own. So encourage folks that are listening to, yes, take advantage of our resources. This will help you, and so you don't have to create the lectures yourself. Now, with that, I do want to spend, as I shared, the bulk of today on showing JMP. And so I'm going to shut off my camera. Andrew, you can do the same. And I'm going to go back to sharing my screen. And sorry, before we leave, Ross, you're kind of monitoring the questions, any coming in that we think Professor Hoff can address?
Oh, we have kind of a technical question that came in right now that I'll handle offline. And so I
Okay.
guess for the sake of time, I suppose you continue, but I think I'll just quickly voice appreciation for you, Professor Hoff. Thank you so much for actually giving us your time and some of your insight today. And hope you're all right if we forward any additional questions we receive to you if folks are interested more in exactly how you've created this certificate program.
certainly, it's my pleasure, and I'd like to say how thankful I am to the suggestions that you folks have made when I was developing this material.
Okay, great. So I am not going to be able to get through every topic that I think is important to learn about in terms of capabilities that JMP has. But each one of these topics, there's going to be a data set and a document that I'm going to open up that is either one of our case studies or one of our enhanced data sets. And you'll see when I open these up what they are. And so some of this you can go through on your own. So if I don't get to cover every topic here, you'll be able to do some self learning. And of course, we're always available for questions. So I'm going to go to this first example where I'm going to illustrate some statistical process control. And this is one of our case studies, and I'm going to just show you what it is first. And so this is one of our resources, and what we do is we create this storyline. And so this one happens to be about studying variability in an etching process. And so the way these are set up is they describe the background of a problem, sort of describe what it is we're trying to solve. And what this one is about is a company is putting together some new production lines. And so this is early stage development. and they're trying to monitor the etch rate and understand the variation in etch rate. And so like every process, there's targets and specifications, and we describe what the data collection process is. And for this example, there's a set of production lines, and each whoop, sorry, just lost it. Basically, what we're going to do is we're going to sample from this batch of 20 wafers each run of the process, and so we're going to oh, sorry, that keeps on changing there. Apologize. We're going to sample 5 wafers across 40 different runs of the process, and we're going to measure the etch rate on different locations. And basically, what this is all about is studying variation in this process over time. So the way our case studies work is they'll illustrate a bunch of analyses. And what's being illustrated in this particular case study is one of the lines is being studied. And not only is it sort of phrasing a question, showing some analysis output, but there's also the jump instructions that are shown to create that particular analysis or graph. This one's talking about some control charts. Again, shows you the steps, what kinds of questions we can answer. I'm scrolling too fast. I know. I just want you to see what it looks like. So this one's also teaching about capability analysis. And then the way these case studies end is it provides a set of exercises. So these are things that you can maybe give out as class assignments or team projects. And so this one it demonstrates analyses on one production line, and then the exercises are all about analyzing it on the remaining production lines. So I'm going to slide this aside for the moment, and I'm going to open up the data set. Okay. So we're going to focus our analysis on just this one production line, A. And so I said we're measuring etch rate. And so each run of the process, you can see we're going to sample 5 wafers, 1, 2, 3, 4, and 5. And so each run, you'll see that we have those 5 wafers. And something else that's happening is after 20 runs, the engineering team actually recalibrates the equipment. So if you scroll through here, you'll see after 20 runs, starting on run 21, the line was stopped and there was some recalibration. And so we're going to try to see how the variation in etch rate changes across these runs and the different calibration stages, and also across the wafer. Now, I have already the analyses saved. So when you get this file, you'll see a bunch of analyses saved. Now, some of the steps I'm going to do, I'm just going to show you the output. And then other ones, I'm going to actually show you how to do the steps in JMP. Some of the folks here are going to be new to JMP. So the first thing I'm going to do, and I always like to do this when I've got a variable like this, is let me just summarize it. And something you can do in JMP, and I'm going to open up some column properties, is you can actually specify the specification limits and put that down as a column property. And the other thing you see I have checked here is show as graph reference line. And so what's going to happen is any graph I make with etch rate, it's going to draw reference lines there. You don't have to do this. You can make the reference lines later, but you might find this easier, especially if you can do it each time. So I'm going to start off by using the graph builder. And so those that are new to the graph builder, think of the graph builder as this blank canvas waiting for you to build a graph. So I'm going to drag variables into different places. I'm going to put this on the x-axis down here. Now, JMP's going to start off with a particular graph. In this case, it does a dot plot. I can change it to a box plot, or maybe a box plot and the dots, or maybe a violin plot. But what I want to do here is I want to pick a histogram. Now, the graphs are interactive, and so one of the things I'm going to do is I just want to change the binning a little bit here, because I want to see little narrower bars. Now, you can drag the axes around. I can rescale it. I'm going to have to change the bin back. I can zoom in, zoom out. Let me get back to changing that. And so see the spec limits are drawn on that graph because I told Jump to do that. And so you can see there's a lot of variation. It kind of goes right up to the lower spec limit and the upper spec limit. In fact, there's even some values that are beyond the spec limits. Now, there's things you can do in here, like I can actually do a t-test and show some summary statistics, but instead of doing it here in the graph builder, I am going to launch our distribution platform. And this is the platform when you're going to do a univariate analysis. And it could be a categorical variable or a continuous variable. And in this case, we have a continuous numeric variable. I place it here in the Y column. Now I'm going to turn this off because I'm going to show process capability a little bit later. And so I don't want to distract us here. So you click OK, and Jump starts off with some initial output. In this case, it's a histogram. Again, notice the spec limits are drawn. Now, all the graphs you get in a report, you can resize. So I just did that to make that a little bigger. Now, this particular platform, it starts off with some things like some summary statistics. So that's added by default. Now, for those of you that are new to Jump, basically, when you run a particular platform, I want you to think of it as you've launched a platform. This is not static output. I've launched the distribution platform, and now I can drop down various red triangles to do different things. So just to illustrate something, let's say I want to do a hypothesis test on the mean, and I'm going to test if the mean is equal to that target on this process. Click OK, and notice this output just got added to the report. And here's another red triangle. Now, for those of you who are teaching things like hypothesis testing on the mean, what you'll love is we have some interactive tools. I'm going to launch this one. So here's where you can teach students what a p-value is. And notice I can drag this around. I can specify the null distribution, what the sample mean is. I can change the sample size or the standard deviation. And so I can teach this concept of a p-value. And there you see the t-test statistic as well. And we also have an interactive tool to teach power. So here I am again, I can move around the null distribution, the alternative distribution, and now I can teach the concept of a type 2 error and power. So you'll see a lot of these interactive tools in Jump. In fact, we have a whole set of tools that are used to teach statistical concepts. Unfortunately, I don't have the time to go into it, but we have webinars that focus exactly on that. Okay, now, because I had those two calibration stages I mentioned, anytime you run an analysis in Jump, almost all of the platforms in Jump allow you to do this. Not every one, but most of them. You have the opportunity to put a by variable. So if I put this categorical variable calibration stage in the by variable, what it's going to do is it's going to create two analyses, one for calibration stage 1 and one for calibration stage 2. So you might find that handy for doing comparison analyses. Now, a couple other graphs I'm going to make, and I'm just going to open one of them up here, is I am going to make a dot plot that is showing every etch rate value for each run. And so I'm going to just slide this aside and show you how I make this graph. Again, this is the graph builder. So I'm going to put etch rate on the y-axis this time. And then I'm going to start bringing in other variables. So if I bring in run and drop it down here, so now I'm going to see all the measurements made for each run. So remember, we have 4 etch rate values for 5 wafers in each run. Now, what might be handy is I'm actually going to put the calibration stage as a color variable. So this just makes it more obvious, the 20 runs for calibration stage 1 and the 20 runs for calibration stage 2. Okay, I'm going to slide this aside or close it. Oh, for those of you who are brand new to Jump, when you want to save this graph to your file, and I want you to keep an eye right there, I'm going to go into the red triangle, save script to data table. You give it a name. I'll just leave it as the default. And when I hit OK, you'll see it gets saved right in that little red box I made. There it is. So you close it, and whenever you want to see it again, you just click the green triangle, and it opens it up. Okay, for this particular one, I wanted to focus on control charts. Now we have two ways to make control charts. We have something called the control chart builder, which basically acts like the graph builder. You can also choose specific control charts in this control chart menu right here. And what I'm going to do is I'm going to use the control chart builder. And as I shared, it looks just like the graph builder. And now I'm going to start dragging the variable into the different places. Now, if I pick up etch rate and put it on the y-axis, jump by default is going to make an individual and moving range chart. Because I haven't told it anything about subgroups, but I want to tell it things about subgroups. So for example, if I put in run and drop it in the subgroups, now I'm just going to zoom this in a little bit here. Now I'm going to get a X bar and an R chart where I've got the mean and the range of the 20 measurements made on each run. Now over on the left, you'll see all sorts of controls. So for example, maybe I want the control limits to be based not on the range, but the standard deviation. And I want the variation chart not to be the ranges, but the standard deviation. And I can choose that. And so it's redoing that. Now, maybe I want to look at the mean and the standard deviation, not for each run, but for the run and the wafer. So now this is going to be the mean and the range of the 4 measurements made on each wafer. So again, I can play around with that. Now, you might have noticed I closed it, but because I told Jump the specification limits, by default, it does a capability analysis. And so over here on the right, I see the capability analysis, all the common metrics that you might be familiar with. Again, this is sort of giving an assessment of how well this process does to specification. Now, there's a really great tool, interactive tool in Jump in the process capability platform. It's called Interactive Capability Plot. I'm going to open that up. And this is really a helpful tool for teaching the concept in class. Because what I can do is, so you see all the capability metrics, but what I can do is change things like the spec limits. So I can move the spec limits around. I can also move what if the mean of this data moved around or the variation changed, and you'll notice all of those capability metrics are changing. So when it comes to the concept of teaching what a capability analysis is, I think it's really great to sort of do a little bit of what if scenarios. What if the process moves by 2 standard deviations in one direction? How will the capability metrics change? Or what if you move the spec limits or change the variation? Or how much smaller does the variation need to be in order to, say, achieve a certain level of sigma, like 6 sigma? Okay, so for the preservation of time, just because I have a lot of different tools I want to show, I'm going to close this up and I'm going to move to a new example. And Ross, I see some questions coming in. If you can handle them, that's great. But if you need me to stop, let me know.
We have one that you might be able to answer in just a quick moment here. One that I'm afraid I don't really know the answer to. So one of our guests is asking specifically about short run control charts. Is this something? Do you know? Is this something that is used in the semiconductor industry, or maybe typically the manufacturing lines are producing the same product over long periods of time, and then short run control charts just aren't relevant? I know you know more about the industry than I do.
Yes. Now, I haven't seen it, but it's not that I work in the semiconductor industry. It would surprise me if it's not. Now, where I have seen it more frequently is I used to work in the printing industry, and what would happen is a printing press may produce, maybe running for a couple hours to do a particular print job, and then it switches to a completely different kind of print job that has different specifications, different process parameters. And so in the course of a day, a printing press might run a handful of different jobs. And so as opposed to monitoring a process day in and day out as it's the same, well, the process is different. And so it would run short. It would surprise me if those tools are not. I just can't give you a specific example. I've just seen it in other applications where the machines are producing many, many different parts and are switching frequently. Okay. So the next one I'm going to go to is sort of doing some comparisons, and what's going to be most interesting is I'm going to show you how we can look at variation on a wafer. And I have two examples here. I like them both, so I'm going to see if I can squeeze these both in. Now, these examples happen to be our resource called enhanced data sets. And so these are similar to the case studies in the sense that it describes a problem. It's going to tell you what jump platforms and statistical methods it's going to use. This one happens to be about studying an oxidation process. So it describes, in this case, what the furnace is and how wafers come in on the boats and gas goes into the furnace and it grows this thin film on the wafers. And so it describes how we're going to sample. So we're going to sample at different places in this boat, different wafers on the far ends and some in the middle. And this picture here is showing you we're going to measure the oxidation, basically the thickness of the thin film at all of these different locations. And what's different between the enhanced data sets and the case studies, it doesn't demonstrate any analyses. It goes right to the exercises. And so you'll see there's a question asked, or there's an analysis or graph that's asked for you to create, and then you'll see the jump instructions are right there after each exercise. So similar to the case studies, you can use these in class to give out as an assignment, or maybe you want to use it to demonstrate. Okay, so I'm going to slide this aside, and I'm going to open up the data set. Okay, so basically what we have here is there's a set of runs on this process. And for each run, we're going to sample 4 wafers, and they're in 4 different locations, 1, 2, 3, and 4. We're going to measure oxide thickness on all these different positions. And the positions are defined by these 2 variables, the x coordinate and the y coordinate. Now, I'm going to jump right to, let's see, thinking about, again, I'm looking at the time. And so I'm going to jump right to, I'm going to open these up instead. Well, I'll do this. I'll save time by just opening them up. So similar, I made a histogram. I can see how it compares to the spec limits. And what you'll notice is there's a bunch of thicknesses that are below the lower spec limit. Now, I don't know if you see this, but when you highlight data in a graph, that data is being highlighted in the data table. So if I scroll through, you'll see some of these rows are selected. So I selected them from the graph. And one of the things I'm going to do, and I'm going to do it in a different place here, because what I did is I wrote a little formula, and I'll open it up to show you. So I wrote a little formula that basically is saying if the oxide thickness is outside of those spec limits, identify that. And I created this column. Now, there's nothing above the upper spec limit. There's only data below the lower spec limit. But if I click on this, those rows are highlighted. And what I'm going to do is I'm going to do this thing called a row state. And I am going to change the symbol to be an open circle. And so what's going to happen, let me scroll down and show you. So every one of those rows is now going to use a different symbol when I create a graph. And so I'm going to start off with showing some box plots. And here's where I'm plotting against wafer position. So notice, see those little open circles there? Those are data points. Well, if I maybe it'll make it more obvious if I change it to a dot plot. So you can see those points right here. Now I can, this is obvious. I can see there is some differences, but if I wanted to do a formal statistical test to see if there was difference between the locations, I would launch JMP's bivariate platform, Y by X. And so I would put oxide thickness there, wafer position as my X. Jump starts off again with some initial output. In this case, it's a plot. And then I drop down the red triangle, and here are the kinds of analyses I would do. So if I wanted to do a one-way ANOVA, I could click on means ANOVA, and then I'm going to get this output. If I wanted to do, say, multiple comparisons, I could go in there and do that. So you see how it's an interactive platform. I just keep on adding analysis output. And so this is output doing a student's t-test, doing every comparison. Now, I know you're probably thinking like, well, wait a minute, you've got run in there and it's not just wafer position. You're right. So if I wanted to do a multi-factor ANOVA, I would launch JMP's fit model platform, because here is where I want to put in two factors. So run and wafer position. And some of you who are familiar with ANOVA, you might say, well, maybe I want to think of run as a blocking variable, or maybe I want to think of run as a random, because these runs are just random sample, where wafer position is more fixed. You can go in there and do that. So you can define if something's a fixed factor or a random factor. And if I do this analysis, I'll keep it as fixed, just because I can think of it as I'm just thinking of it as a blocking factor, because what I really want to do is I want to study if there's a significant effective wafer position by controlling for variation in runs. And so now if I did, say, multiple comparisons, for example, on wafer position, and now what I'm going to get is now it's controlled for the fact that the runs might be different. And again, there's all sorts of output here. Oh, I'll point this out. If you're looking at output in JMP, up at the top in your toolbar, you have a little question mark. And if you float your question mark over different pieces and click on this, what it's actually going to do is launch our help documentation for that particular output. And so here I sent myself to the doing multiple comparisons in the ANOVA platform. Okay, now I'm going to open up two graphs here. Well, maybe I just need to open up one. I'll open up one here. So here is where I made a box plot for each run and each wafer position. So you'll notice the wafer positions are the panels and runs are down the bottom one. And I can switch that. So if you right click on the title of a variable, I can go here and say, well, let me swap it out. And if I do this, now I have wafer position as the X variable and run as my panels. And everybody should be able to see, no matter which graph you look at, you can see, you can see that as I'm going across the runs from 1 to 12, it tends to be going down. And when I go from wafer position 1 to 4, you can see that same pattern. But the reason why I brought this example up is because I'm going to show you how I can incorporate the X and Y coordinates in here. And so what I'm going to do is I'm going to drag the X and Y coordinates in here, and JMP starting off by just showing me, well, the X and Y coordinates. I haven't told it anything else yet. But what I'm going to do is I'm going to say, I'm going to put wafer position here, and I'm going to put run up here. And I'm going to resize this so it actually looks like a symmetric circle. And I'm going to take oxide thickness and I'm going to make it the color variable. And so now, in this case, now I can change this. In fact, I always like to change these. I always like to change this so it's on a quantile scale. And this way, in this case, gray is the 50th percentile, the median. And then as it gets lower, it's blue. And as it gets higher, it's red. I can change those colors if I want, but I'll leave it there. Now, what I want you to notice is there's an extra level of variation we're now picking up. And I made it more obvious by, remember when I changed those points that are outside the speck limit to be open circles? You see all those? And if you look, you'll notice where they tend to occur is on this lower right-hand side. It's not in every wafer position. It tends to be more in the wafer positions 1 and 2, but you'll notice that there's this extra level of variation. And that is essentially what statistics is. I had a professor who used to say, statistics is the science of studying variation. That's basically what it is. If things didn't vary, the subject wouldn't exist. And so in this case, I'm studying variation across wafer position, variation across runs, and then because I have this XY coordinate, I'm studying variation within the wafer. So I have those different levels of studying variation. Now I'm going to close this up and I'm just going to quickly open up the next one. I like this one. This is another example of using location. And so this one is about studying the performance of each of the little chips, so the integrated circuits on a wafer. And so basically, as these wafers are being made, there's electrical testing being done on each of the ICs. And again, this is one of our enhanced data sets. So there's all these exercises with jump instructions. And I am going to open up that data set. And in this case, I'm going to go right to the graphical representation of location. So there's a bunch of analyses I could do. In this case, the outcome is categorical. Either the chip passed or failed the electrical testing. And if I went and did the distribution platform on test results, remember it's a univariate analysis is your distribution platform. I've got a categorical variable. Well, it's going to go in here and produce some output that you would do in this case for a binary variable. If I drop down the red triangle here, well, these are different things I could do as compared to the numeric continuous. Why? Well, because I got a different kind of variable. So, for example, I could put confidence intervals on this if I wanted to. I could even do hypothesis testing on the proportion if I wanted. And I can do comparative analyses. So in this case, I have batch 1 and batch 2. And so I could use the fit Y by X platform. I'm going to do test results by batch. And well, in this case, since I gave it a categorical Y, the default is basically going to be contingency table analysis, a chi-square analysis, and I can do basically comparative analyses between the test results between batch 1 and 2. Here's my little red triangle. All sorts of things I can add to this. So I could do 2 sample tests of proportions, risk differences, odd ratios. For the preservation of time, I'm not going to do that, but here is where I can do all sorts of analyses when I've got a categorical, in this case, a binary outcome variable and a categorical X. But the reason why I wanted to bring this example up is because, again, I've got XY coordinates. And what I'm going to do in the graph builder is I'm going to drag the XY coordinates into here. Oh, sorry. I'm going to put in my XY coordinates. Okay. Now, those XY coordinates are basically the location on a wafer. And I'm going to put the test results as the color variable. And what I can do now is, now this is using all of the wafers. That's why you see different gradations. It's not just blue or red. Oh, and by the way, you can change these colors. So if I wanted to go in here and say, well, if it passes, I'll make it green. And if it fails, I'll keep it red. That's kind of a nice thing to do. Now, what I can do, and you can do this everywhere in JMP, is I can open up something called the local data filter. And now what I can do is I can say, well, I want to filter by wafer. And now what I'm going to have over here on the left is now I can move through and filter the data for each wafer. So if I click on wafer 1, now the only data being used in this graph is the data from wafer 1. And so now it's binary, passed or failed. And I can just move through each of these wafers and look at, now you probably just saw that, but when I went from when I basically went from batch 1, which is the first 25 wafers. And then as soon as I go to batch 2, watch how the number of passed and failed changes. Okay, so you can see how much of a poor performer this process is for that second batch. Now, another way I could have done this, I'm going to remove the local data filter, is, and this is similar to what I did in the previous example, is I'm going to put wafer up here and batch over here. Oh, I should do, hold on, let me resize this. Sorry. Oh, I want to do, okay, so let me resize this. So now, that's going to take a little bit of time to get this exactly the way I want. But now I can see the individual wafers if I wanted to look at them all together. So this concept of location is really great because now I can produce sort of a heat map of each wafer and using a binary variable. So I think that's really handy in JMP that you can do that. Okay, so now as I shared, I'm not going to be able to go through every one of these examples because of time, but the other ones here, there's one here on a measurement systems analysis. So this is, again, if you open that up, it's an enhanced data set with exercises and the whole storyline and along with the data. But what I'm going to do is I want to go to our design of experiments example. So I got another one for linear regression. Again, I'll let you go through that on your own. And so this one is about running a designed experiment where we're going to measure a couple variables in basically this chemical vapor deposition process. And we're gonna run an experiment where we're gonna control 3 variables. One is going to be gas flow. We're also going to vary high frequency power and low frequency power. So there's 3 variables, and we're going to study a full factorial with center points. And so here's a little diagram of that experiment. Okay, so we've got 8 runs on the corners. We're going to do some center points. And if you notice here, we're actually going to do 2 runs at each of the corners and 4 runs in the center. And as I shared, there's a storyline, a description of the experiment, and then it jumps into some questions showing JMP instructions to run an analysis to analyze the results of this experiment. And let me move this aside here. Now, what I'm going to do first is show you in JMP how you create an experiment. And so we have a whole DOE menu. I mean, I think this is one of JMP's best platforms. I think we're the industry leader in design of experiments. And so what I'm going to make is I'm going to make a full factorial design. And so it starts off with this dialog box where it's basically waiting for me to tell it what the experiment is. And in this data set, we actually have 2 response variables. We have average thickness, and here's where I can say things like, oh, here's a target, and I've got some specifications on this. So you can, you don't have to, but you can identify this. And later, when you're trying to optimize the outcomes, it takes into account what you define here. There's also another one which is trying to minimize, and this one is the variation thickness. So again, you specify the outcome variables, and then down here, you're going to specify the factors. And so I have 3 factors, so I can actually create this all in one step here at 2 levels. And then you go in here and type what the factor name is and what the levels are. So it happens to be studying gas flow from 240 to 300. I have high frequency power, and I'm going to study that between 750 and 850. And I have low frequency power, and I'm going to study that between 180 and 260. You hit the continue button, and then here's where I'm going to define things like, well, am I replicating the experiment? In this case, I'm going to replicate it once because I want 2 runs at each of the corner points. And I'm also replicating the center point. So I'm going to put 2, and that's going to give me 4 center points. And then when I say make table, JMP is going to make the table with the experimental design that I outlined. Now I'm going to close this, and I am going to open up this file. So when you get this journal, the file that I have here is with the outcome variables. Now, because I've got a multi-factor experiment, I'm going to be building a multi-factor NOVA model, essentially, and that is using our fit model platform. And so you basically give it the response. I can do both at the same time. I'm just going to do one, say average thickness. And I'm going to choose the 3 factors. And I'm going to tell JMP that I want to, for this first analysis, I want to study the 3 main effects and the 3 two-way interactions. So when I click run, JMP is going to fit the full model. I told it that. I said, fit a model with the 3 main effects and the 3 two-way interactions. And one of the things you typically look at is this table at the top where I'm going to see test for each of those terms I put in the model. Now, remember, I say that this is an interactive platform. So I can start reducing the model right from the report. So for example, I'm going to take out this interaction because it's not significant. There's my little p-values over there. So when I click remove, it takes that out. I'm going to remove this next one, take that out. Now, right now I've got basically the power, those 2 power variables as an interaction. So that tells me I have to leave these in no matter what the p-values are, and I've got a significant gas flow. Now I'm going to close up a bunch of these analysis tables that pop out here. What I want to draw your attention to, if you haven't used the fit model platform in JMP before, is you do a lot of cool things here, and specifically, you can create visual representations of the model that you have fit. And so I can open up this thing called the profiler. And so now I have a profiler that I can interact with. I can either drag these around or go in and type in numbers where I can see the effects of those factors. Now, notice the interaction there. See, as I move this around. Now, aside from this being a great way to analyze, I think it's an awesome way to teach, because what is an interaction? Well, it says the effect of a factor is a function of the other factor. So if you look at, say, the slope of high frequency power, well, the slope is different depending upon where I am for low frequency power. So it's a really great way to get students to understand this idea of an interaction. If you look at gas flow, which isn't involved in an interaction, the slope doesn't change. Now it shifts up and down, but the slope isn't changing. So this is where you can help students understand there's no interaction there. You can also, if I wanted to see I can do interaction plots. Those are common to do when you're showing the effects, especially with the interaction. I can do a surface profiler. And so now I can see basically the response surface I fit. I'm going to add some things here. I'm actually going to add the data points. I like to make these a little bit bigger here. So, I know I'm moving pretty quickly, but whenever you're dealing with a report in JMP, if you want to know if it does something, basically either right click on the output or double click on it, and that's where a menu will pop up to show you things. And so there's all sorts of controls I can do here. Like I can put contour plots on this graph. Same thing, I can kind of resize this and rescale this if I want. Now you might be looking at that saying, well, that's not going through the points, but remember, I've got 2 levels of gas flow. And so if I switch to gas flow, now I can see how it's fitting that particular variable. There's even contour plots. So if I wanted to see a contour profiler, I can do that as well. So at JMP, we believe every analysis, whether it's basic or advanced, should come with visualizations that communicate the results. Now, I know I went through this very, very quickly, and there's some examples I didn't do, the measurement systems analysis and the linear regression. But again, you can go through this on your own. There's an enhanced data set with the exercise steps and the data sets that it comes with. So I encourage you to do that on your own.